scalar product of two vectors. In this module, you will learn to find the scalar product of two vectors. The scalar product of vectors A and B is defined as the product of magnitudes of vector A, vector B, and cosine of the angle between them. Dot is the operation symbol for the scalar product. The scalar product of vectors A and B can also be interpreted geometrically. If a perpendicular is drawn from the end point of vector A onto vector B, then OM represents the orthogonal projection of vector A on vector B. Now, consider the right triangle OAM. The ratio of the base to the hypotenuse, that is, magnitude of vector A, is equal to cos theta. This equality helps us to deduce that the base of this right triangle is magnitude of the vector A into cos theta. Thus, the scalar product of vectors A and B is the product of magnitude of vector B and the scalar component of vector A along vector B. Similarly, dot product of vector B and vector A can also be obtained by multiplying magnitude of vector A and the scalar component of vector B along vector A. The dot product of vector A and B can be obtained by either multiplying the projection of vector A on vector B by magnitude of vector B, or by multiplying the projection of vector B on vector A by magnitude of vector A. This fact helps us to conclude that the dot product of two vectors is commutative. Remember that the angle between the two vectors is formed at the point of intersection of the initial points of the two vectors. In some cases, we may need to shift a vector along the line of support parallel to it to obtain this point of intersection among the vectors. If you are given two vectors A and B intersecting each other at the initial points, then the angle between them is given by cos inverse of vector A dot vector B upon magnitude of vector A into magnitude of vector B. The dot product of two vectors is maximum when theta is equal to 0, as cos theta will have its maximum value 1 when theta is equal to 0. This fact helps us to conclude that dot product of unit vector I cap with itself is equal to 1. Similarly, j cap dot j cap is equal to 1 and k cap dot k cap is also equal to 1. On the contrary, the dot product of two vectors is equal to 0 when theta equal to 90 degrees, as cos theta is 0 for theta equal to 90 degrees. This helps us to derive that dot product of unit vector I cap and j cap is equal to 0. Similarly, j cap dot k cap is equal to 0 and k cap dot I cap is also equal to 0. The dot product of two vectors is minimum for theta equal to pi, as cos theta has minimum value, that is, -1 for theta equal to pi. This fact helps us to conclude that dot product of two vectors is negative of the product of their magnitudes for theta equal to pi. Some more properties of scalar products are as follows. If A, B and C are free vectors, then the dot product of vector A with the sum of vectors B and C is equal to dot product of vectors A and B plus the dot product of vectors A and C. This property is known as distributivity of scalar product over addition. Next, if A and B are two vectors and lambda is any scalar, then the dot product of lambda times vector A and vector B is equal to lambda into dot product of vectors A and B, which is further equal to dot product of vector A and lambda times vector B. In this module, you have learnt that the scalar product of two vectors A and B having angle theta between them is given by magnitude of vector A into magnitude of vector B into cos theta. When dot product of vectors A and B is given, the angle theta between the vectors A and B is given by cos inverse of vector A dot vector B upon magnitude of vector A into magnitude of vector B. Dot product of two vectors is commutative. Dot product of unit vector I cap with itself, j cap with itself and k cap with itself is equal to 1. Dot product of unit vectors, that is, I cap dot j cap dot k cap and k cap dot I cap is equal to 0. Dot product of two vectors is negative of the product of their magnitudes when the angle between the two vectors is equal to pi. Dot product of vector A with the sum of vectors B and C is equal to dot product of vectors A and B plus the dot product of vectors A and C. Dot product of lambda times vector A with vector B is equal to lambda into dot product of vectors A and B, which is further equal to dot product of vector A and lambda times vector B.